Hello and welcome to lesson 1.4, inverse functions and logarithms. So today what we're going to do is we're going to review some of our skills with inverse functions and how they work out. And we're also going to talk about how we can use logarithms or find inverses of certain exponential functions using specific types of logarithms. So first off, we're going to determine the inverse of f of x equals x squared. Okay, we're going to do it both algebraically and graphically. So first off, let's draw y equals x squared. Oops, sorry, that's in the wrong spot. So here's an example of y equals x squared. And its inverse, we'll draw as well on the same axis. And we'll just label this f inverse of x for the time being. So actually I'll change this to just f of x. Okay, so as you can first see, your original function actually is a function, and because it passes the vertical line test, so let me choose a different color here. Here you can see passes a vertical line test. However, the inverse is not a function. So f of x is a function. F inverse of x is not a function. Okay, so let's find the equation of our function f of x. So to find the inverse, you usually let y equal f of x, then you switch the x and y variables. Now technically this is the inverse, however, it's not usually written in this format. We usually isolate for the variable y. So I'm going to square root both sides. If I square root both sides, I have to count for positive and negative. So that means f inverse of x is actually made up of two functions, positive square root x and negative square root x. So you can see that one is a function and one's not. The inverse is not a function. Okay, so this leads us to, what if we were looking at the inverse of f of x equals the square root of x? So let's draw that. You guys might start to see where I'm going with this. So if this is our function f of x, we can find its inverse by drawing it. So I can draw that. Right here. So this is the inverse of f of x. Well, let's find the equation of such a thing. So again, y equals the square root of x. Swap the x and y values. Solve for y. You get x squared. But the issue here is this drawing of f inverse of x in blue is not what we get as our equation. This equation y equals x squared actually describes an entire parabola, whereas our drawing is only part of a parabola. So you have to make sure that you're actually stating the domain as being x greater than or equal to 0 here. You could include the range That's not necessary. But there comes in the fact that this original function f of x has a domain, specifically, or is defined on for x values greater than 0, and a range with y values greater than 0. It's particularly this range right here that gives us our domain of our inverse. So you have to also look into whether or not the actual inverse is actually the correct function specified, and you might have to give domain or range restrictions in order to be more careful. And in this case, you can actually see that these two expressions are actually functions. So both f of x in this case and f inverse of x are functions, where f inverse of x just turns out to be that x squared, where x is greater than or equal to 0 specifically. So this comes to this idea. A function f of x is considered to be called one-to-one on a domain D if f at a does not equal f at b whenever a does not equal b. So in other words, what we're looking at is whether or not the inverse is also a function. So some ideas right here is, for instance, a function like this is not one-to-one, because the value f at a and f at b right here are the same values for different values of a and b, and that's not allowed. So what we can do is we can use what's called the horizontal line test to verify if a line crosses at most one point on a function f of x, and f of x is said to be one-to-one, and that means its inverse is a function. And a function f of x has an inverse g of x that is also a function if and only if f of x is a one-to-one function. And then looking at what we talked about earlier about composite functions, that means f of g of x would actually equal x. And same thing with g of f of x would also equal x. So for instance, in our second example, our functions f and f inverse would follow this property. But in our first example, it would not. Okay, so now coming to logarithms, how can we use logarithms to help us out? Recall that a logarithm is an inverse of an exponential function. Now, we were introduced to this e, this Euler's number. Well, as a function, this function is called the natural function, natural exponential function, or Euler's function. So if you take y equals e to the x, you can actually find a function that's exponential, and that's somewhere between y equals 2 to the exponent x and y equals 3 to the x, leaning more towards the y equals 3 to the x. Its inverse is described as y equals ln of x. So in other words, this y equals ln of x is actually equal to log to the base e of x. Now, they don't often use log to the base e of x. They consider that improper form, okay? And this means y equals e to the x has an inverse, or sorry, my apologies, also means or implies that x is equal to the natural logarithm of y. So these are actually inverses of each other. So what we can do is we can now solve things with lns and e's in them. Please realize on your calculator, on any calculator, you should be able to find, scientific calculator, you should be able to find an e and a ln. In order to access the e, usually it's a second function of the natural logarithm. Okay, which is thing is called the natural logarithm. Okay, so let's solve these using exact values. So to get rid of the e on the left-hand side, we apply a natural logarithm to both sides. Like so. What happens is it allows you to take that 2x, because it is a logarithm, and bring it down in front. Now, because ln and e are inverses of each other, it actually cancels each other out and gives you a value of 1. So now we're working out the natural logarithm of 10. And we're going to divide both sides by 2 to get x as the natural logarithm of 10 divided by 2. Please realize that ln of 10 divided by 2 is not equal to ln of 5. You have to apply the function first to the value 10 and then divide by 2. Now, if you want, you could find the exact the approximation of this using a calculator if you wanted to. So this could be approximately, using my calculator, I get 1.5, oh sorry, 1.151. Okay, so we're going to do something similar to this other one. Okay, in order to get rid of a natural logarithm, what you want to do is you want to apply its inverse to both sides. Again, a similar property allows you to cancel the e to the ln and make it just equal to 1. A little bit stranger is that this now becomes 3 to the x as just a base value. So in order to solve for x, you just take e to the 5 and you divide by 3. Again, using our calculator, we can approximate this to be approximately 49.471. And that's how you solve for functions with e or ln in the actual equation. And thus concludes this lesson.